This is multivariable calculus, and in this video, I'm going to talk about section 14.2, limits and continuity. So as we go through this section, what you're going to see is that a lot of the topics that we cover here are going to be very much like what we talked about in 2 dimensions, except today we're going to be talking about those same ideas in 3 dimensions. And so the first one we're talking about here is the idea of a limit. And this is just the definition of a limit. And you may or may not remember back from Calculus BC when we talked about the definition of a limit. We got into the whole idea of the delta epsilon definition. And in the end, the main thing we talked about was in order for the limit to exist, the left-hand limit had to be equal to the right-hand limit as we approach some point. So that's essentially the same thing that we're saying here in 3 dimensions. And I'm not going to break down all of the notation here, but you can see we're kind of talking about the same thing, where this time when we talk about the delta, we're talking about the difference in the x and the y values. And when we talk about the epsilon, we're still talking about the difference in the function values. So the difference here, though, is we're not just approaching a point from one side of a function and another side of a function. There's not 2 ways to get to our point. There's actually an infinite number of ways for us to approach a point when we're talking about a 3-dimensional graph. So what we have to do is we actually have to consider approaching that point from all directions. And if all of our limits from all directions are approaching the same value, then the limit will exist. If all of them do not approach the same value, then the limit fails to exist. Now, there is some notation here that I want you to notice. We have slightly different notation because we've got more variables. So you can see here it says the limit as xy approaches a and b. And where before we would have seen, the limit as x approaches a or whatever it happened to be. So now we have to consider that we're approaching in both the x and the y direction at the same time. Okay, so we can write that in a couple of different ways. Here's a couple of different notations. So we can write the x and the y separate here with the limit as x approaches a and y approaches b of that function. Typically, I'm going to use just the coordinate notation, but you can also write it out. The function approaches the limit as xy approaches ab. Okay, so let's take a look at graphically what exactly we're trying to represent here. So graphically, what we're looking at is we're approaching that point from all different directions. So for example, if we were trying to take the limit here, that's the point where we're trying to find the limit. And you can see from above, we've got this sort of overhead view. From above, we have all these different paths tracing along the surface that we have defined here. And along any of those paths, it's leading me to the same point, which means the limit would exist. Now, obviously, if they didn't all lead to the same place, the same function value, then at that point, the limit would fail to exist. So it's a little bit harder to evaluate these, but it's still the same basic idea as when we talked about limits in 2 dimensions. Okay, so let's take a look at an example of how we would evaluate these. And we don't necessarily have to go through such a long drawn out process like we will here every time, but this gives you a feel for how this works. So we have a figure below that is the function negative xy over x squared plus y. And we have sort of a unique situation happening at the point 0, 0. And so that's what I want you to see here. So we've got this function. And you can see that as we approach the point 0, 0, there's some weird stuff that's going on at the point 0, 0. And I can kind of predict that based on this function. If I plug in the point 0, 0, I'm going to get 0 over 0. So I know there's the potential for this limit not existing because of the fact that I have this, in this case, indeterminate form that is occurring when I actually evaluate the function at this point. Okay, so let's take a look at how would we evaluate this limit? Now, to actually prove that a limit exists when we're working in a multivariable setting, we actually have to go through and do a formal proof. So for us, unless it's continuous, so that would be the one exception. If it's continuous, we can just do substitution. We can show the limit exists. So for us, though, typically what we're going to do is we're going to show that a limit fails to exist in situations where we see these kind of unique points. Like I said, if we want to show that a limit does exist, if it's continuous, it's very simple. If it's not continuous at that point, then becomes a much more complicated process where we have to start getting into proofs, and it's really beyond the scope of what we're going to do in this course. Okay, so let's say we wanted to take this limit as we approach the point 0, 0. What we're going to do is we're going to take different paths to that point into account. And you can see I've got 5 different paths listed out here. The x-axis, the y-axis, the line y equals x, the line y equals negative x, and the parabola y equals x squared. And what we're going to do is we're going to figure out, okay, when we approach along these different paths, are we getting the same value every time? So this would be the limit as xy approaches the point 0, 0 of f of xy. In this case, that would be equal to the limit as t approaches 0 of f of t 0. And let me explain where that's coming from. So we're going along the line y equals 0 if we are approaching on the x-axis. So that's why I'm using the limit as t approaches 0 of f of t 0. So when I do that, what I'm going to do is I'm going to transform this function into a single variable, which then will allow me to evaluate the limit. And if I were to plug t0 into this function, f of xy is negative xy over x squared plus y squared, what it simplifies down to is the limit as t approaches 0 of negative 0 over t squared, which then that is equal to 0. Okay, so we found a limit as we approach the point 0, 0. We found a limit as we approach along the x-axis. So let's do the same thing along the y-axis. So along the y-axis, same idea. I'm going to write the limit as xy approaches the point 0, 0. And again, it's f of xy. Well, this time along the y-axis, I'm essentially going along x equals 0. And the reason that I'm writing that is because that tells me that this is going to be the limit as t approaches 0 of 0t. And that gives me the limit as t approaches 0 of same thing, negative 0 over t squared, which again is just 0. So far, it looks like this limit could possibly exist because along 2 different paths, I'm getting the same value. But let's do this another way. So now let's go along the line y equals x. So again, I'm going to take the limit as xy approaches 0, 0. And I know it's kind of tedious to keep rewriting this, but it's helpful because you get used to writing the notation and reading the notation. So remember this time, if we're along y equals x, that means the x and the y values are always the same. And this is where that t, the idea of substituting the t in, becomes really useful. So we're substituting this parameter in to turn this into a single variable limit. So this would be the limit of, and I forgot my f up here, f of tt, and that would be the limit as t approaches 0. Now remember, we're going to plug t in everywhere we see x and y here. So you can see we're going to get negative t squared over 2t squared. Okay, so this will be negative t squared over 2t squared, and that would give me negative 1/2. Okay, so immediately at this point, I know this limit doesn't exist. The reason I know this limit doesn't exist is because going along these 3 different paths, I've already found a different value along one path than I found along the other 2. So as long as one of them is different, the limit no longer exists because they all have to be the same. Along any path that I take to this point, I should be getting the exact same value. And in this case, you can see I'm not. Okay, so let's go ahead and evaluate these last 2 just to get a sense for how this works. So this last one, or this next one, I should say, we have the limit as xy approaches 0, 0 of this function. In this case, it would be the limit as t approaches 0, and it's the line y equals negative x this time. So I'm going to use t negative t. And that would be the limit as t approaches 0. In this case, we're going to get t squared, positive t squared over 2t squared this time, which would be 1/2. Okay, so we got another different value. So clearly this limit doesn't exist because we keep getting different things as we're approaching 0, 0 along these different paths. But let's just do one more. And I want to show you one more because sometimes you can't just use really simple paths to show that the limit doesn't exist. Sometimes you have to look at your function and figure out, okay, what's something that I can choose that I think is going to make me get a different value than I got before. Now, let's say I'm looking at the 1/2 and I want to figure out what can I do to make something different than 1/2 show up. Well, in this case, we're going to use the parabola y equals x squared. So we're going to take the limit as xy approaches 0, 0. And that would be of the function of f of xy. That would be equal to the limit as t approaches 0. And in this case, we have y is equal to x squared. So my x is t, and then my y is t squared. And that's equal to the limit as t approaches 0. And in this case, I would get negative t cubed over t squared plus t to the 4th. Well, in the end, I can solve this thing out. And in the end, what's going to happen with this is if let's see, I could divide out some t's here, and I'd get t over 1 plus t squared. And in the end, I'm going to end up with 0 for this one. Okay, so which matches up with the first two that I got. But if I had started with the line y equals x or the line y equals negative x, now I've shown a different path. I got a different value. Okay, so clearly this limit doesn't exist. And you can kind of see that. The point that you're looking at on this graph, just to be really clear, you can kind of see where they've drawn in some of the paths here where we're approaching different values depending on the path that we are taking. Okay, so definitely some weird behavior going on with this function at that point where we had that indeterminate form 0, 0. Okay, so that's sort of the idea. When I ask you to solve a limit, it's either going to be direct substitution, it's continuous, the limit exists, or you're going to show me that the limit doesn't exist by showing me some different paths where they don't necessarily match up. Okay, so here's an example that I want you to try. It says, if this is our function, does the limit as xy approaches 0, 0 of this function exist? Now, notice I put a graph of the function here so you could get a feel for it. Notice at 0, 0, it looks a little bit strange. Anytime you see that odd behavior, that should be an indicator. It looks like this limit may not exist, but I want you to try to find two different paths that will make this limit fail to exist. So go ahead and pause the video. Try to just do two limits. Try to do one that gives you a value, and then try to do another limit that potentially gives you a different value to show that the limit doesn't exist. Okay, so let me show you the way I did this. I chose the limit as xy approaches 0, 0. It's not always going to be the point 0, 0, but we're just using this for the sake of making this sort of simple. This would be the limit as t approaches 0, and I have to decide on a path here. So I'm going to do along y equals 0. Okay, if I go along y equals 0, that means it's f of t0, which would be the same as the limit as t approaches 0 of 0 over t squared, which is just 0. Okay, so that one gave me 0. So now what I want to be thinking about is what can I choose for a path that's going to give me something different? And so when I looked at this, I thought, okay, well, how can I make this come out to be something other than 0? Well, to make this something other than 0, if I could get a t to the 4th expression to show up in the numerator like it's going to in the denominator, then potentially I could make this come out to be a non-zero value. And so what I did for my path then is I said, all right, let's take this limit. The limit as xy approaches 0, 0 of f of xy is equal to the limit as t approaches 0, and The path that I'm going to use is I'm going to go this time along x equals y squared. And the reason I chose x equals y squared, again, is because I want to make a t to the fourth show up in the numerator and the denominator. And if I do that, this is going to end up being f of t squared t. And that would be the limit as t approaches 0 of t to the fourth over 2t to the fourth, which is 1/2. So I got 1/2, which is different than the other limit that I got. So I can say, therefore, this limit, as we approach the point 0, 0 for this function, does not exist. So DNE for does not exist, just like we did in 2 dimensions, still works the same way. Okay, so I've shown that that limit fails to exist. And again, if I want to show a limit does exist, much more complex if I don't have a function that's continuous. All right, so let's talk a little bit about the idea of continuity, because I keep bringing that up. So continuity in 3 dimensions really is essentially the same thing as continuity in 2 dimensions. When I talk about continuity, I'm still looking for the limit value to be equal to the function value. So for us, when we look at continuity, before, when we looked at it just sort of tracing along a function, we'd say you could draw it without lifting up your pencil. Well, now we're going to be looking for these, sort of unique features that are happening where you can see the function value kind of dropping off and jutting up or down at a point. That's going to indicate to me that it's potentially not continuous. The easiest thing to identify is there's no function value there, then I know it's not continuous. Sometimes, though, we have a function value and then we need to evaluate the limit. Okay, but notice here for this definition, the limit value is equal to the function value. That's how we define continuity. Same stuff we've been doing for the last, year plus or 2+ years, depending on how long you've been doing calculus. Okay, so there's also some stuff here about continuous functions and working with continuous functions. And if we have a function that's continuous and we look at another function that's continuous and we multiply them, we still have a continuous function. If we have a composite of continuous functions, we still have a continuous function. And same thing when we're dealing with parametric equations. If the pieces are continuous, the overall function is going to be continuous, and so on. Okay, so let's take a look at a few examples of continuity. So it says evaluate this limit, and then it says, is the function continuous at the point 1, 2? Well, notice in this function, all we have are polynomial terms. If all we have are polynomial terms, just like in 2 dimensions, polynomials were continuous everywhere. Works the same way when we're dealing with 3 dimensions. If I have polynomial terms, that means this will be continuous. So since, let me rewrite that there. All right, so since my function f of xy is a polynomial, it is continuous everywhere. Okay, so we've got a continuous function. Well, if I want to evaluate the limit, remember I said we can only evaluate the limit if we know the function's continuous. Well, now if I want the limit as xy approaches 1, 2 for this function, and I'm just going to write it as f of xy, that would be equal to, just plug in 1 for x and 2 for y, and you'll see that you got 11, which is the same as f of 1, 2. And that's because it was continuous, we knew the limit had to exist. Okay, so let's look at another one. It says evaluate the limit as xy approaches -1, 2 of xy over x squared plus y squared. Is the function continuous at the point -1, 2? Well, if I look at the point -1, 2, I can see that I'm going to get an actual function value. I can also see the composite of this is going to be continuous. I don't have any points. If I broke xy over x squared plus y squared, if I broke that apart into pieces and I took the limit of xy as I approach negative 1, 2, and I took the limit of x squared plus y squared as I approach negative 1, 2, I can see both of those are continuous. So I know this function is going to be continuous. So that's all I'm really doing. So is this function continuous? Yes, it's continuous. And if I wanted to, I could say f of negative 1, 2 is equal to negative 2/5. So in terms of my justification, I can justify it really in a couple of different ways. I can say when I plug the point negative 1, 2 in, I get a function value. Therefore, I know this is continuous. But you can also say, I can look at the pieces of this function, and the pieces are continuous. So the composite of that is also going to be continuous. All right, so when we talk about continuity at boundary points, remember when we were dealing in 2 dimensions, when we did continuity at boundary points, we had kind of a special rule. We would say that if in order for a function to be continuous at an endpoint, then the function value had to equal the one-sided limit value. Well, in a similar way, when we're doing continuity at boundary points, we don't really have endpoints, we have boundary points when we're dealing in these multivariable functions. So at boundary points, we have kind of a special rule. And the special rule is we treat our boundary points to be these sort of arbitrary points, x naught, y naught. And x naught, y naught are the boundary points for that domain. And if we can show that the limit value is equal to the function value at those boundary points, then we know the function is continuous. So it's pretty simple to do. You can see what we've done here is we've taken the limit as xy approaches x naught, y naught for this function, square root of 1 minus x squared minus y squared, which is a hemisphere. We've plugged in the point x naught, y naught. We got the square root of 1 minus x naught squared minus y naught squared, which is 0, which is the same as the function value. So in that case, then, it has to be continuous at our arbitrary boundary points. Okay, so pretty simple to do. We won't do that a lot with continuity at boundary points, but if you need to, it's still the same idea as the limit value equal to the function value. You're just considering the boundary points, though, in that case. All right, last thing here, I put some special limits on here. So there are some special situations where we can evaluate limits of multivariable functions. And it really only works in certain circumstances where we can do some substitutions that allow us to essentially treat these as single variable functions. So notice what they asked you to do here. It says evaluate the limit using substitution z is equal to x squared plus y squared, and observing that z is approaching 0 from the right if and only if x and y are both approaching 0, 0. Okay, so for us then, what that means is I can rewrite, see this first limit, the limit as xy approaches 0, 0 of sine of x squared plus y squared over x squared plus y squared. I can rewrite this based on their given information as the limit as z approaches 0 from the right of the sine of z over z. So now I've rewritten that as a single variable limit, which I know this is equal to 1. You either have that memorized or you could use L'Hopital's rule at that point and solve it out. Okay, same idea on this next one. We've got this x squared plus y squared, which seems really complicated because I'm going to have a negative 1 over 0. But if I do my substitution, I'm going to get the limit as z approaches 0 from the right of e to the negative 1 over z. And now as I approach 0 from the right, I'm essentially going to get e to the negative infinity power, or e to a negative very large in magnitude number, and that's going to approach a value of 0. Okay, so probably could have figured that out without doing the substitution there, but you get the idea that if you can get these in terms of a single variable, it becomes very easy to solve these things out. All right, so let's take a look at one other type that we can solve. So we can also solve these limits sometimes by converting to polar coordinates. And what I mean by that is we know r is equal to square root of x squared plus y squared, or we know r squared is equal to x squared plus y squared. So it says to evaluate these limits by converting to polar coordinates. So we have this limit as xy approaches 0, 0, and you can see that if we did direct substitution into this, we would actually get 0 times really 0 times infinity or 0 times an undefined value. So what I need to do then is I need to think about the fact that r is equal to the square root of x squared plus y squared. So what that basically tells me is r approaches 0 from the right if and only if xy approaches the point 0, 0. So that's the substitution that I'm going to use. So what that means is my limit as xy approaches 0, 0 of this function, and I'll just call it f of xy for now, is the same as the limit as r approaches 0 from the right. Well, the square root of x squared plus y squared becomes r, and then we have the natural log of x squared plus y squared. Well, that's the natural log of r squared. Okay, so right now we've got essentially 0 times infinity, which is what we had before, but now we can actually use a technique to solve this, because we know that we can go through and we can do L'Hopital's rule here. So what I'm going to do is I'm going to rewrite this as the limit as r approaches 0 from the right, and I've got 2 natural log of r over 1 over r. You may or may not remember that from when we did L'Hopital's rule in MVC calculus, but what I'm trying to do is make either 0 over 0 or infinity over infinity show up within my limit so that I can apply L'Hopital's rule. In this case, we got infinity over infinity. So now I can take the derivative. So I'm just going to say it's equal to, and I'm just going to write LH to indicate that I've used L'Hopital's rule on this step. The limit as r approaches 0 from the right, and I would get 2 over r when I take the derivative of the numerator, negative 1 over r squared when I take the derivative of the denominator. In the end, that would give me negative 2r squared over r, which is going to end up approaching a value of 0. So I got a value of 0, even though initially I didn't really have a way that I could approach that when I got one of those indeterminate forms. So I was able to use polar coordinates to convert it into a form where I could then use L'Hopital's rule. All right, so last one here. So I want you to try this one, and then I'll show you my solution. So just pause the video, work through this problem using the same idea, and see if you can come up with the solution for this limit. Okay, so using the same substitution as what we just did, I can rewrite this as the limit as r approaches 0 from the right. X squared is the same as r squared cosine squared theta. And I know that y squared would be r squared sine squared theta. And when I said use the same substitution as we did before, I just meant use polar coordinate substitution. So we're converting the x's and the y's into expressions involving r. Square root of x squared plus y squared is r. So in the end, this is the limit as r approaches 0 from the right. And I would have r cubed cosine squared theta sine squared theta, and that is going to end up giving me 0 times 1 times 0, so I'm going to end up with 0. Okay, so again, a situation where initially I had 0 over 0, I could convert it into my polar coordinates. When I divided that r out, I sort of removed the discontinuity in that graph, and that allowed me to solve the limit. Okay, so the big thing to remember as you work through the problems in this section is that we're just trying to get a feel for all of the basic calculus ideas that we talked about in 2 dimensions. We're trying to now understand those ideas in 3 dimensions. So as long as you have a good understanding of the conceptual ideas behind limits and continuity in 2D, remember we're just extending those ideas into a 3-dimensional setting.